But let's get going. All right, we are on our review lecture 15 for midterm on Thursday. This thing is impossibly long. I always feel like I have to apologize for it. There's no way we're going to get through all of it, but it's all here in one place. If you want one slide set, you just want to come through. I mean, maybe we'll get through it, but I don't want to, fly through this so fast that nothing gets absorbed. But we'll see how far we get. And we're starting at the back with the old stuff, so maybe that's the best thing to do. And if we miss the more recent stuff, then that's maybe not so bad. A couple quick announcements though. Let's see. Don't forget about blackjack. It's due on Tuesday when we get back. I know that's kind of a little bit rough, but it is one of 7 that we need to have by the end of the semester. We will drop 2. So there's 9 out there, including potions. So if somehow you're just like not feeling this one, you can pick up potions later on. But basically, you got two homeworks you can drop out of the 9, and this one's not too terribly bad, but I know we're coming up on the end of this first half of the semester, and everybody wants a break, and everybody deserves a break. So hopefully that's you can find an option in there somewhere. Potions is really great if you want to really get good at maps, so keep that one in mind. Quiz 4, of course, ungraded. Don't forget about that. Midterm practice is out now. That's a good look at what's coming on Thursday. And I don't want to say it's not hard, but I do think if you got some experience and some focus, you'll find it to be more straightforward than some of my other exams for sure. Um, if you do, just letting you know, if you go back and you reuse your quizzes and you get a better score, I got to set that back. Totally fine. I do want you to use your extra quiz tries, but I need to just make sure your grade is the highest grade you had when you submitted. So don't let that scare you away from using them if you want, because that's really what they're there for. And then 5:40 on Thursday, please come in a little bit early. Try Zoom if you want to be able to ask about a problem question where something is broken or there's a problem. But we'll have about 170 minutes, 50 questions, and you'll know exactly what kinds they are from that practice. So definitely make sure you take a look at that. The corrected answers, like always, won't be available until noon after the day of the exam. So really, I think some places I've said Saturday, but I think I'll have them by noon on Friday, and you should be good to go if you're curious about that. Midterm grades all the grades are pretty much up to sync, except for a couple. Apologies for taking a little longer this weekend getting stuff knocked out. If there's something you're worried about, send me an email and I'll take a look at it. Please make sure I don't have any questions outstanding for you in Canvas. Sometimes those things get away from us, me too. So feel free to let me know. If I've screwed up a grade and it doesn't factor into your official midterm grade that I'm supposed to post, happy to go back and fix those things in Canvas. And of course, you'll get credit for that toward the end of the semester. So the more stuff we can clear up now, the better. So maybe take a quick look if you get time for that. If for those of you who are using Replit, I am going to ask you to turn off your AI. Just maybe make sure you know how to find it in the lower left corner of your window, and you want to uncheck the enable box. They keep changing this. At some point, maybe it's never going to turn off. But I would feel better if you guys are familiar with how to turn that thing off. I'll ask you to do that the day of the test as well. Couple other things just real quick before we get going. Just quick announcements. One, the Mesa Center is looking for embedded tutors for next semester for the fall. So if you think you might be interested in that, maybe reach out to myself, or if you know Nicole, please reach out directly. But let me know if you think you might be interested in that. And that's for CS and of course all other subjects as well. But you guys are the most advanced students I have, so you probably, some of you, if you enjoy it, would be good educators. The other announcement is just totally off the wall, but Program IZ is expanding what they're doing into algorithms, and so many of you have taken the algorithms course, And so they're doing automated, or not automated, but simulated sorting algorithms to help students that are taking Comp 220 type courses. And so they are looking for feedback from actual students. And so I have access to links for some of the sorting algorithms like merge sort and quick sort stuff we covered before. And they just would like your honest feedback. So they're basically trying to decide, yes or no, do we launch this as a public part of our service? And so they would value any perspective you have. So if you're interested in that, drop me a note. I'll put an announcement also in Canvas. So as a reminder, but it's probably like 10 minutes of, perspective and a quick, yeah, good, no, here's the problems I see. So anyway, I put that out there for you. Let me get our door and then we'll jump in real quick. All right. Okay. So let's jump into operator precedence. And we won't go over the really basic stuff, but the one that's tricky is just the pre and post increment. So I think we've talked about this before, but if you've forgotten, remember that plus plus after the B means we increment it after we take the value and assign it to A. So the plus plus happens after the assignment. So it's like just a shorthand for A equals B and then B equals B plus one. Okay. If we put it beforehand, it pre-increments. So it's just going to do the opposite. And so it's just a tricky way, sometimes a little too tricky to write very concise code, but you want to be aware of that behavior in some of your code questions that might come up. When it's in a situation like that, we really don't care, right? So the I++ can come as plus plus I or I++ because it's at the end of our for loop every time. So please do keep those in mind. And then old-fashioned arrays, not what we would say is a container array, but the old-fashioned arrays, just real quick reminders, we can initialize those, of course. So that means we're going to get 0 through 4. It's going to be driven by that dimension. Of course, we can not assign anything, right? And so if we have variables for this, right, we can have an R and a C that act as the dimensions for those declarations. The other important thing to remember as coders is that arrays, fundamentally basic arrays, are just pointers, right? So PTR, char star PTR equals S is a perfectly legal way to kind of steal the pointer from S. So S as an array refers to the first or 0th position, and PTR essentially just does the same thing. So we can do some interesting things with pointer math. Like we can say, okay, what is the location of PTR plus 4? So the plus 4 is plus 4 character spaces. So the compiler knows that we're saying plus 4 based on the type. So if this was an integer, that's a much bigger data storage. So it knows to kind of hop over based on the type of the array we're actually dealing with. So we can do crazy things like if S square bracket 4 equals what's at PTR plus 4, and they should very much be the same thing, okay? And then we can also literally use the address to assign things. I can say, go to that location and put what's at that location there or compare it to what's there, right? That would be kind of silly putting the same thing in the same place, but I could say, hey, is this equal to that? And that should be true as well, okay? So those are just some basics, a little lower level stuff. You should understand how to loop through 2D arrays as well. We've done a little bit of that, a lot more of that coming. And really think about the outer of those double for loops as being the row iteration and the inner one being the column iteration. And you should generally stay out of trouble if you can do that. Now, when we pass two-dimensional or n-dimensional arrays into a function, we have to at least declare and lock down the column dimension. So keep that in mind. That'll kind of clarify how you're going to write some of your functions when that comes up. The first one, we can leave it out, right? And then it's just up to the function to decide how far it goes down the rows. And it could crash, or maybe we pass in another argument that says how many rows we're passing in. But we can leave that out of the declaration, which is kind of nice, okay? Now, in terms of arrays, before we had the string data type, all we had was C strings. That was just an array, essentially, of a collection of characters. But there were some weird variations on that. So fundamentally, if we aren't using the string class, and even the string class does this, it's really just working with arrays of characters. So chars 5, for example, uninitialized, or that's really initialized plus unknown to a lot of people, we get a little extra character on the end of that. It's like a little stopper so that when we're printing this thing out, we bump into, or C out bumps into the \0. And that's how it knows how to stop when we're printing something like that, okay? So that has an extra character that we might not really realize. Now, something we're gonna do a lot more after the midterm break is dynamic allocation. So here we're saying create a dynamic collection of 5 characters, give me the pointer, and I'll hold on to it. And that's really just an array, right? So that's just a dynamic way of creating that on the fly. And maybe that 5 was 5 million or 2 million. We don't know until runtime. And so that's a lot of the times why we want to do dynamic allocation like that. Okay. So still S is a pointer, just like the S up here. It just happens to be pointing to some dynamically allocated memory. Now the weird animal is const char star pointer, right? This is actually a pointer to a character. It's kind of like an array, but it cannot be changed. It's a special location in memory. We'll talk about this a little bit more after the midterm as well. But it's just another way to create a string. And we are not going to really test you on this in the midterm, but it's just part of this whole family of things that we talk about when we talk about arrays or collections of characters. It's just kind of a strange alternative. And it can be treated like an array. I can say char pointer square bracket 0, char pointer square bracket 1. I just can't change it. I can only read that information. Okay. So that's just a little really old school background on the collections of characters there. Now, in general, we should all be getting a lot more comfortable with pointers. We're going to do a lot more with pointers after the break. So we want to be able to understand the difference between dereferencing, that is following a pointer, and taking the address of or getting the pointer for a variable. So here's a variable. There's me taking the address of the variable and holding on to it in an int star type variable. Okay. So here we have a yellow, I call it the yellow star. It's in the type side of things. But when I have this green star, I know it's kind of hard to see on the screen there, but that's the dereference. It says put 5 at that location, at where a pointer is pointing to, okay? And so if we have a function where we say, hey, here is the address of A, that's me taking the address of A and passing it into the function, okay? And of course, that function better be expecting to get an address of that particular data type. Otherwise, things are going to go badly, okay? Which is the same as just saying pass in a pointer, okay? So hopefully all these things kind of make sense. And then the trickier one that maybe we're getting a little more comfortable with is like, hey, is that pointer pointing to an instance of a class? If so, then we can use the arrow to go directly to a member of the class. And that's only if it's pointing to a class or a member or an instance of a class, okay? So if it's not, and it's just the actual class itself, then we use the dot. So understanding the difference between these two is something that we hopefully will, everyone will be comfortable with, okay? Uh, so we'll see that in some questions for sure on the practice midterm and on the midterm. Now, just trying to put it all in perspective on one slide, if we create a variable A and then we create a separate variable PTR, right? We haven't aimed that PTR at anything. That's me aiming PTR at A, of course. And that is different. I say that's on the right-hand side. This RHS is my abbreviation for right-hand side of the equals, right? We're over here taking the address of something. On the left-hand side, as part of the type, is a different animal. We don't see this too much. I'm saying, hey, B is now an alias for A. They are the same variable, in fact. So what we're really doing is just sort of like going, hey, I'm the A too. So whatever we do to A, we do to B and vice versa. It's a weird thing. It's not a pointer. It's a reference, and most languages have references. C++ has pointers and references, which makes it a little bit of a unusual language. So here, putting something in B is exactly the same at putting it in A. And we'll talk later in the semester about why and when you would use references versus pointers. But references are pretty good. They just don't get you all the way to where you need to go. So that's why pointers is usually a requirement for a CS kind of a core curriculum at a four-year institution. Okay. So the star, just to review that real quick. So if we create a pointer type, then that's going to be int star, float star, whatever. It's on the left-hand side, or LHS, okay? So this says PTR equals the address of A. That is different than the D reference, which is saying, hey, Q should get what PTR is pointing to, okay? So sometimes seeing both applications on the same page helps kind of sort out the confusion. It took me quite a while when I first started coding to kind of separate these ideas in my head. Okay, but I tend to think about the yellow star on the left versus the green star on the right. Not always true. Obviously, on assignment, we're over on the left side, but hopefully those things are starting to sink in a little bit. Functions. So general topics, right? Obviously, you should know how to define a function and what it means to return or not return a value, and that bad things can happen if you don't return a value. So the compiler is generally getting pretty aggressive these days about warning us that there might be a situation where you didn't return a value. We're going to be getting into some homework assignments where that can be really hard to debug. So if you see that warning, in this class, I am a little less tolerant of code that gets submitted with that warning. It's like you should do whatever you got to do to make that warning go away, because it could be a sign of a real serious problem in your code, okay? So in that case, of course, we never returned our final false there, so our final Boolean. Okay? Now, overloading, I know we cover this a lot, so most of us have probably seen this many times, but overloading functions requires that the arguments be different, okay? So the return value alone is not enough to overload a function. So here we have two translates that take a string argument, one argument, but one of them is a string return and one of them is a char star return. That is going to trigger a compiler error. So we can't, that's not enough of a difference in order to have those two exist at the same time, okay? But the idea, of course, is just making our brain space a little less cluttered by using the same name for multiple flavors of the function, okay? And you can take a look at some sample code there if you like. Default arguments, we've seen them all over the place. So the key thing perhaps to remember is that they go with the prototype. So if I have a function with default arguments and I'm putting it in a .h file, or I'm putting it at the top of a CPP file, put your defaults with the prototype or the .h in that case. And then, of course, we kind of know the meaning of that, right? Once we provide that value, we can then take it inside of the function, and we can call the function, with 1 or 0 arguments or 2 arguments if we want. Just that's the benefit of that. Okay. Now, the whole idea of passing by reference versus passing a copy or passing by pointer, these are tricky subjects for beginning intermediate coders. So let's take a look at our pass by reference. So it's a way of allowing a function to change one of its arguments directly, okay? So here we have to return a value. So if somebody gives us something, we end up returning it because the value we were given is not a reference. It's just a copy of some number, okay? So adding our special ampersand now means typically we see a void with functions like that because it's like, oh yeah, I can just do it this way. So it's kind of like an alternative way to return a value, but we're really just changing that thing, okay? But pointers accomplish the same thing too, right? So I can say, hey, this is a pointer. It's kind of like a reference, You might think, yeah, why both of these things, right? It's a tough, I mean, usually most people get queasy over this, right? So they'd rather go with a reference and just say value equals value times 2. But if value is really a pointer, I should have called this PTR. I'm saying what's at PTR equals what's PTR times 2, okay? So we're still changing it, but we're changing it indirectly via pointer instead of reference. So that's the difference between those two kind of, right? And of course, otherwise, it's just a copy. Always, always, always a copy of whatever kind of data type is being handed in there. Okay. Access types we will use more and more, especially as we create hierarchies of classes later in the semester. But we should, for classes in general, understand how to create a class from scratch. So we should all be able to say class A, curly brace, semicolon. That's the simplest class we could ever make. So we should all be able to know how to create something like that. We should know how to create a constructor and initialize our data members. And if we don't initialize our data members, bad things can happen. We'll look at some subtle examples of that here, I think, on the next slide. So here's our person class, and I have a data member over here called age, and then I have one called string. So age is uninitialized and random. We should consider it as random. Oddly, though, string is not. And so you might think that's annoying, but it turns out that string is a class. So last name is an instance of a class, and it's calling its default constructor. So like any good class, it should take care of business for us. And so it does. And so it has a nicely initialized blank string inside of it. So we don't want to get too comfortable with strings because our primitive data types obviously need to be initialized. So if we haven't done it there, we got to do it in our constructor. And so knowing the difference between the data members and the arguments of the constructor is kind of a critical first step in being able to write these kind of classes, okay? So I think most of us have seen that. And I think we'll see here in a minute, but we could also say this arrow first name. We'll review what this is, but you can always just take the shortcut and just use the data member. If you're inside of the class, you can reference it by name directly, okay? So that's our kind of beginning. And of course, watch out. I know it happens a lot, but sometimes people get confused because of this semicolon here. They get in the habit of moving this semicolon outside of that, right? And then you get compiler errors, or they add an extra one just in case. We really don't need a semicolon after our functions, right? Or after our constructor, okay? We just need it at the bottom of our class definition there, okay? So it doesn't hurt you, but it does confuse the discussion a bit. More on constructors. So everybody should understand what it does, that we can overload it if we want to. We want to avoid confusion by using the same argument names as our data members. That's a very dangerous thing to do. So we generally try to avoid that. Sometimes we'll put an underscore in front of the argument to make that different, more clear. And then just remember that the return value for a constructor is essentially an instance of the class. So what they're doing is always returning something like a function. It's just an instance. So we don't really have to like say what they're returning. We just kind of understand that that's what it is. So here's our constructor with our arguments and our references to our data members there, okay? Now, multiple constructors, of course, same as overloaded functions. So different argument lists are required. And there are some situations where you might get into some confusing things. If you have something that has one argument and something that has one argument that's the same type with a reference, the compiler might scream at you and say, hey, that's a little too close, right? So you can figure that stuff out with code pretty quickly. But normally, if you've got a different number or organization of argument types, then your constructors can coexist together, okay? So how do we use those things in main? So most things are pretty straightforward. The only thing that surprises people sometimes is putting the rounded parentheses after that would be a mistake if there were no arguments in it, okay? The only time we do that, and I know it's confusing, is when we need to call the class name directly with no arguments so that we can dynamically create an instance of a class. We'll do a lot more of this in the second half, but obviously here we're getting a pointer back, and here we're actually getting the actual instance of the class. Okay. So a little confusing there, I know, but we want to be able to instance our classes. We want to know kind of what that means, right? The class is a factory cranking out instances. So it's like a car factory or any kind of a grommet factory, okay? So there's really a difference between the instance and the class. And then the members of the class are the data members, but also the functions are considered to be members too. So we call those member functions, or I like to call them methods in C++, but they are members of the class as well. Okay. And so just a heads up, when we do something like this, foo f parentheses, it thinks that's a prototype for a function that returns the type foo. So that's why that doesn't work. So if you find yourself looking at a multiple choice question, that's going to be a bad answer if you're trying to create an instance of f, right? Because the compiler can't really tell that's an instance of f, which is one of the reasons why we don't have those extra parentheses on there. Okay. So when we talk about a default constructor, it's just anything that doesn't have arguments. Okay. So there again, reminder at the bottom on how you do that. So we don't pass anything in because there's no arguments right here, right? So that's a pretty easy thing to do. We can, of course, add a message here to say hello world or whatever, but that's an example of our default constructor, okay? And then our default arguments, just like we saw with our functions, we gotta set them. And so as tedious as it is, we kind of gotta say argument goes into data member, argument goes into data member, right? So this is the manual way to do it, okay? Even though I gets its value from here, we still gotta, of course, make that connection, okay? So there's our data members and our assignment, okay? And then we can go ahead and call that with as many arguments as we want, right down to nothing if we want, okay? But that took us to our constructor initializer list, which does not go in the .h file, and it does not go with the prototype. It goes with the definition of our guts of the method, if you will, or our constructor. So we're going to put that thing off to the side. We'll look at the format for this in a second. But of course, it just serves the same purpose as what we saw inside, right? So over here, instead of this, we're just moving it over there. And it's a single colon, right? And then kind of it's like breakfast equals B, lunch equals L, dinner equals D, right? But it's just a different way to accomplish that as part of the constructor definition. Okay. Okay, and then similar to that, we can stack our delegate constructors on there, right? So we can say something like this in a base constructor, and then have some specialized constructor that says call the base constructor via the initializer list, and then continue on to override something, okay? So there's lots of ways to save code that way, so we're not writing this same stuff all over the place, which is kind of tedious. Okay, so that's our delegate constructor. And if you try to call the delegate constructor in here like it's a function, feels really good, but you get some weird errors. So you want to avoid that and just put it on here, okay? We've had some very, very strange bugs in here for that particular reason. Okay. Operator overloading, really cool feature of C++, really is just like overloading a function or overloading a constructor, but we get to overload symbols. So we've looked at a handful of these, and we'll go deeper in the second half of the semester, but you want to kind of be familiar with the syntax and be able to read code that is overloaded and see what it is doing. So being familiar with that will kind of avoid the deer in headlights effect, right? But basically, the big ones are plus, minus, times, and divide. And we should know that what we're really doing is defining the meaning of plus for a particular class. So our fundamental data types already know how to add themselves together, etc., right? Those are just part of the language, but we're defining it as the meaning for a particular class, right? So let's say our class is animal and we have two instances, dog and cat. We got to figure out what that's going to be, okay? But we kind of did something a little more obvious, which was create our own wrapper around a number and then just did something like that, which is really cool. It looks like normal code, and in theory, it just works. So we can make our classes really fully featured. I like that idea of like writing a class and adding all the bells and whistles. So it's just fun to code with, you know. So that's our number class overloading. Okay. Now there's a couple of things that we need to remember. So here's our operator plus, operator minus, operator star. Those are the names that we use for the method name. It's really no different than any other regular method name. This is just me coming up with a name called toString. So this is just a normal method. We're just kind of defining what it means when we encounter that plus, okay? And in this case, we're returning some new instance. So the actual instance is coming back that we can use for something else, okay? And then whatever arguments and whatever body of our code there. So if we look at one of those things up close, here's an operator plus equals. Now this one's a little more special because it's actually changing and returning something, and we at the same time, right? We're actually changing ourselves. So we're saying, hey, add something to me, right? So that's the name of what we're calling. Here's what we're given, some other instance. And I'm going to say me, my value is what I am plus this value. And then when we return it, we're going to return an instance of the class. Okay. So notice that when I say number, that's an instance of the class. And this is an instance of the class. So taking a dereference, this should really be green actually, to use my own colors correctly. Dereferencing a pointer to this instance returns an instance of the class. If I said return this, that would be a pointer to an instance, and that doesn't match, right? That would be a number star. So what does this thing right here mean? That basically just says, hey, don't make a copy of yourself when you return it. Just return a reference so that someone else can change you as well, okay? So this is some really special sauce right here that allows us to do LHS plus equals RHS. It can have like, you know, a chain of things all together, which is pretty weird code, honestly, but it allows you to do that, and it allows you to minimize the number of copies that are created, okay? So that's okay. Star this is okay, and that ampersand there is generally a very good thing to do for returning stuff that you want somebody else to change. It's going to minimize the number of copies that are getting created, okay? So that's the general model for things that not only change themselves, but also want to let other people change them too, okay? So a bit out of order, let's review what our this is. When you are inside of a class, it's kind of like you're working on a car on an assembly line at a car factory. When you're working on an instance of the car, this refers to the instance that you're working on, okay? So it is always a pointer. That means this arrow gets you to the data members of the class, okay? So if that's our pointer, this arrow X gets us to one of the data members. But it's optional, right? We don't really need to use it. So you might think, well, why should I use it? It does help remind you of what's going on. Sometimes you forget you're inside of a class. But this is where we really need it, right? We just saw that on the previous slide. We need to get a copy of ourselves, like taking a picture, like a selfie, basically, and then handing that off to somebody else, okay? And that's what we were doing in that last slide, sending back a reference or a copy of us. So if we want to be tricky, we can say, oh, well, then dereference me in parentheses .y. That's just a different way of doing this. And you don't really see it very often, but it should make sense. Get a picture of myself. Oh, now I'm the instance. So I will say dot data member, right? So I could do this or anybody else could do that. We usually do it this way, right? But that's we could get rid of the arrow and all live life this way in C++ and things would still work, right? Pretty much. Okay. So just comparing two instances, right? This is just a good thing to consider, right? If I want to know whether these two things are comparable, especially when we think about functional objects, right? Or functors, we talked briefly about for sorting. It's like, how do I compare two things and sort them? Well, we have to write a comparison function. So if my val is greater than N2's val, let's say, then I know that one is greater than the other. So in this case, the way I use that is I'm going to say one dot is greater than two, okay? Because I'm the one using my method to compare against the two, right? So the two is what comes into here. We could turn that around and say is two dot is greater than one, right? And we'd get a different answer to that, okay? So here's the visualization of that. I know this is probably unnecessary, but if I'm working on this instance over here, I have access to these data members. Obviously, they're going to have different values than over here in this instance, okay? And this is the factory, right? So this is just the factory that produces these instances, okay? So this never really refers to anything back at the factory. It's always the particular thing we're working on right now, okay? Okay. Let's see. Out of class. Everybody loves and hates this. It's just a fact of life with C++. If we're going to describe the guts of something with its curly braces and how it works, then we have to specify what class it belongs to. This is the constructor, which I usually put in green to remind me it's kind of like a function. And yellow is the data type. So foo, double colon foo, that's my constructor, right? So that's how we define it, assuming we have a prototype for the class somewhere. Okay, so that's our primary syntax. And then we do not place semicolons after the curly braces, right? I don't know why I threw that one in there. I guess I was seeing a lot of that. So if I create a really, really small class, yes, I'll have a semicolon there. But otherwise, if there's a method inside my class, I don't put a semicolon. I don't know, these things are sort of just thrown in there because I think somebody was probably doing a lot of that one year, so I added it in there. So here is just comparing. So this is our kind of dot H, which is typically referred to as a declaration. It's like we're declaring the existence of a class and all of its methods and data members, but we didn't really come up with a true definition of it yet. So the true definition happens in our CPP file, and that's the out of class implementation, okay? So we talked about doing this so that we can work in large teams of people, which we haven't quite got off the ground yet, but I'm hoping we can do that right after the semester break or the mid-semester break. Okay. And notice we have our defaults on the left in our .h and our constructor initializer list on the right in our CPP. Okay. So hopefully those feel a little familiar. We also talked about friends because classes that, have private data members are not going to let, by default things have access to them. Those classes can declare things to be friends. So here we have a public horsepower, right? But what if that was private, right? So if horsepower was private, then car can't really say e.horsepower, okay? Which is a little bit of a problem. So we just got to add the friend class car inside of the engine description. Okay, so the engine declares car to be a friend, and car doesn't necessarily have any friends. That's okay, but it can reach inside of the engine and still kind of print out its horsepower, for example. Okay, so it reaches into the engine class because the engine class gives it that access. Okay. So anytime you start building things that are made out of other things, we usually run into this problem. And we don't really want to make everything public all the time because that opens the door to accidental abuse in larger companies. Okay. So there we can kind of print out that stuff pretty directly. The other solution is, of course, to just add some getters, some public getters, but maybe car wants to change the horsepower, right? Maybe we want car to be able to change the horsepower as well. Okay, so that's what the friend does for us. So that led to this messy preprocessor thing. So when we talk about library design and libraries in general in C++, we can't go very far without our preprocessor. So when we pre-process, it's just a giant copy paste machine. And these pound things, that's all they really are. They're instructions for the copy paste robot. They're not part of C++. C++ doesn't understand what those things are, and they'll be gone by the time C++ starts compiling our code. So the job of the preprocessor is to just get rid of all that stuff and replace it with code. So let's look at some examples of how we actually could use these things. So the most common one was what we called include guards. And it's a little annoying, but it's the way everything has worked since the dawn of time of modern C++. We say if some variable, and this is not a C++ variable, this is a variable for the preprocessor. It's like, hey, if I've defined this before, if I've not defined this before, then define it. And then here's some code that I want. Okay. So, and then there's the end of the question. So next time this thing is included, right? That in the same file. So I'm a CPP over here, right? And I'm slurping up this .h file. It's like, hey, I want that, right? And then somehow somebody does it again. Hey, I want that again, right? We don't want this code in here twice. So the second time it's going to say, hey, whoa, hold on. This has actually been defined, so don't do that a second time. So we're protecting the CPP file from getting more than one copy of this code in here, okay? Now we wouldn't normally add this dangerous bit of code down here, but that just goes to show you that that code would get included multiple times if it's not protected inside of these guards here, okay? So that's the whole point of those guards, is it only allows that inner code to be included one time, okay? So it's pretty rare that we would see some code down here, okay? So that's our classic include guards, which is messy, and we could have just used pragma once, right? Pragma once is an alternative, cleaner way to actually doing that, okay? We could also use the preprocessor for injecting debug code. If we're debugging, here's some stuff, right? So debug, define it, do some normal stuff, add some debug code for your PlayStation or your Xbox or your mobile phone or whatever it happens to be. And then when we get rid of this thing, we don't have to go cut out or comment out this code. It just automatically goes away, which is pretty nice, right? So you're not uncommenting and recommenting code all the time. You just have a little preprocessor variable up there to add it or subtract it, okay? So that's what our preprocessor is doing for us, okay? Well, there's lots of ways to use it, but we're really mostly looking at this model, right? Lots of .h's, lots of possible inclusions in a lot of different files in a lot of different directions, but the include guards ensure that we only have one .h in each CPP that's unique, okay? So that just works, okay? So we say one declaration per translation unit. So this is what we call a translation unit, translation unit, translation unit. Okay. And why don't we call those CPP files? Well, translation unit is like, hey, it's all ready to go, so we can glue them all together and make an executable program out of it, okay? So the preprocessor turns those things into translation units, okay? Okay. Let's see, that's that. Templates we talked about, so super helpful, and we will do some cool things with templates again this semester before the end of the semester. So this is just another kind of a copy paste machine that happens before actual C++ compiling. So we are getting the computer to write actual C++ code for us not just include it or not include it, but to like expand it into a lot of possible code. Okay. So these are kind of the basic things we should know how to do: create templated classes, create templated functions, and then to call them. And most importantly, to understand what's going on here, we're not, this is not part of C++. We're just saying, hey, could someone else write my C++ code for me? That's what templates are doing. And it's a really nice thing. And maybe someday it'll be, extended by AI. It'll write a whole lot more than it already is. Okay. But right now it's really pretty simple. We're just replacing that queue with some data type. Okay. And the data type that we replace it with depends on how we call our function. Okay. Just like vector int, vector char, we're just saying, hey, that's what I want you to replace. So the copy paste machine just comes in and does that replacement for us. Okay. So that's a templated function, of course. Okay. And then here's a templated function with two different parameters. So this is usually where things get confusing. That's just saying here's one type and here's another type. Let's say that's an int and that's a float, right? So one is the return type and one is the type of our arguments. Or you decide. You get to design that to be whatever you want. So when we call it, we actually have to pass in both types, okay? Now, if this cannot be converted into this, then we will get a runtime error, right? Because we're forcing the integer a. Let's say somebody put a string here. Like, we can't convert an a into a string, so that's going to be an error, right? But we could convert an int into a float, for example. So there still can be some runtime errors that come up depending on what parameters or types get poured in there. Okay. But most of the time, it saves us a lot of writing code, okay? So there's the class example. I think we've seen that a whole bunch of times. Pretty similar idea. Just replace the queue with whatever data type flows in there, okay? And so just like vector, when we create an instance of it, right? So vector int, right? Foo int, it's really the exact same animal, right? We're just saying, hey, write that for me for an integer or write that for me for a float, okay? Which is pretty cool. And when the compiler uh, writes this stuff, it first looks here and it goes, what do I need to write, right? And it says, aha, I need to write one of these with an int and a char. Then it goes and writes two versions of this. So it's kind of based on need. It's not going to write every possible combination. It's just going to write those two right there because that's what it found in our code, okay? Okay, and then over to files, really just review. We should all know how to open and read data from a file. I don't generally spend a lot of time torturing you with complex file formats, but that really is a skill that's worth developing. Some of you've probably done a bit of that. But the most important thing is just to use the modern approach to opening these files. So an IF stream is a data type. Really, it's a class, right? So we're calling the default constructor on a variable or really an instance of this class and feeding it a file name. So the constructor for the ifstream class opens the file for reading purely based on the data type, ifstream, okay? So ofstream does it differently. And we could, for both of them, use the open method of the class, right? So this is a default unopened output file. Now we open something for output, right? And now we can write stuff to that file, okay? So as we'll see for the rest of the semester, all of these instances of classes can sort of masquerade as normal variables, and then we can call methods on them later. That's how everything in C++ works, really, okay? So here's a file name. There's a handle, right? And there's a word that we're going to read from the file. Now we can open it. And this is really the safest way to process a file. While we can get something out of the file and into one or more variables, keep going. And then do something with those variables. Okay? So you could stack up, 3 or 4 or 5 things here, right? Lots of variables that you want to read one after another. if there's 3 things on each line, for example. Okay. Okay, but we're not gonna torture you with all that. Just want to make sure you know how to open those files and close them and read and write basic stuff. Okay. Okay, containers. So getting close, actually. We're not doing too badly. 6:30, yeah, maybe you're doing okay. So remember that there are 3 kinds: sequential, that's like vector, string, array, list, and then the associative ones that we're just starting to get to know: sets and maps and all their different variations. And then, of course, the weird ones, the adapters we finished up with just last week, it seemed like. So you don't need to memorize all of these things. Just look for the high points, okay? So for example, you can't push something back on a stack. We only can push onto the top of the stack. So even if you don't remember the exact names, you should have this concept in your head about, a vector is something I can add to the end. A stack is something I add something on the top, that kind of stuff, okay? And for the questions, there'll be plenty of hints to help you get through that. But here's our sequential containers, okay? Things that are connected or in some kind of order, not necessarily sorted, right? Including string. And then our associative ones, although I don't know if we've seen this, we've said, okay, I can have a set. So there's just a key that's unique and sorted. So you can kind of see it's in the unique keys and ordered area, right? Or I could have not unique keys, so duplicate keys, still ordered, right? And then all the different flavors. So these are the key value pairs we saw recently. And then we just had to come up with names for all these other things. But everything pretty much flows from these 2 things, right? Unique keys, duplicate keys, sorted by order, not sorted. And again, for the algorithms, folks, these are hash tables because they're unordered and very, very fast. And these are binary search trees, okay? Something like that, okay? And then our weird ones on the side there are stack queue and prioritized queue, okay? Oops, a little too fast on that one, okay? So let's just touch on a few high points of these, okay? So they all share these weird iterators, which are really just classes that masquerade as pointers. They're not really pointers, but they have overloaded operators, so they act like pointers. So what do we care, right? As long as we treat them as pointers, then they're kind of easy to remember how to work with. So they have some weird methods. Begin, right, is our first beginning of the iterator, and end, right, is the bumper at the end, right? We get to the end, we've gone too far, right? Which are different than getting the thing at the front of the container and the last thing at the back, right? Those are 2 different things that are often confused. These are iterators. These are actual pieces of data or references to data that we're actually getting, okay? So end is our stopper. So we usually say, well, I'm not equal to the stopper, keep going. So that's typically how we iterate, okay? So here, remember, vec.begin is correct because vec is an instance of a vector, and instances, we use a dot to get access to their methods, okay? Even though what begin gives us is an iterator, we don't say vec arrow begin because begin is a data member of the vec instance, okay? I know it gets crazy when we start thinking of iterators and pointers and all that. Now, if I did something like this, let me clear away my scribbles, and I said, hey, make me a pointer to a vector. I haven't created the vector yet. I've just said, I'm going to have a pointer to a vector soon. And I say, hey, create a dynamically allocated vector, a new one, and then give me the pointer. So in this example, oops, this should be PTR. I would say PTR arrow begin because PTR is a pointer. So pointer to instance, actual instance. So all we got to do is look at the declaration type to know whether we should be using an arrow or a dot. And that should be the only thing we need to worry about. Okay. I gotta fix that one. Give myself a reminder there. Okay. So this was, we'll see this a few times, but we can say, vec iterator q, that's really messy. Or I can just say auto q equals c begin, continue while q is not equal to end, etc. Okay. So this is overloaded, right? Plus plus, this is overloaded. Probably even this is overloaded, right? So all of these symbols are making it feel like a pointer, but it's not really a pointer. Okay. Start at the begin, continue on, not equal to the end, and off we go, right? And at any point, we can use the overloaded dereference to figure out what's at that thing, like we've done in the past, okay? And there's the back. So this is a pretty safe model for iterating across all types, list, forward list, you name it, okay? The not equal to is the safest way to go, cover pretty much everything. Now we can use range-based for loops, or we can use iterators, okay? So a lot of people prefer the range-based for loops because they're just kind of very straightforward, right? But the thing you got to really be careful with these things is you probably want to really understand the importance of references, because you might end up pulling copies out of your container rather than the actual thing. So when we get to our Facebook homework, which is maybe 7, I think, or 6, this is going to trip up a lot of folks. So here I'm saying, hey, get me a reference, not a copy. Okay, so that's going to go really fast. If I wanted to change it, right, I get rid of the const, and now I could actually change the item without taking it out of the container. Okay, so without that, we are just starting to pull copies, and that could be a problem. Okay, so here we're saying, hey, get me a copy of what's in the vector. Okay, and so I can print that out, but if I tried to change it, like say item equals 5, it's not going to change what's in the vector because it's a copy, okay? So typically, we would not make any kind of change there. But we can use this for almost every kind of container, including our old style C arrays, which is pretty amazing. So a lot of people don't realize you can use a range-based for loop on a regular array, which is pretty nice, okay? So here's our vector. Now we're using our reference, which allows us to change the item, right? So item star equals 2, and that allows us to modify the vector, right? So we've actually modified the vector at that point, okay? Super powerful. Just don't forget, think twice about ampersand or no ampersand, okay? Strings we've seen since forever, right? So one interesting thing is, maybe a little surprising, deep down underneath all these things is still a good old friend, the C array. So that actually gets us a pointer to a C array. So you can reach inside of a string and pull out a pointer to a really old school array. It's in there. It's just part of the class. The class is kind of making it nice for us so we don't have to deal with stuff. So we can ask for the length or the size, all the good stuff we know about. And then toString is just a good thing to know about, okay? So if you want to be able to convert any data type into a character array, or sorry, an STD string, like a modern string, you want toString, okay? So there are a lot of old school ways to do this, but this is the most elegant way to actually go about doing it, okay? So a lot of times we need to cobble together a sentence. It has words and numbers in it, and toString comes to the rescue very, very often, okay? Because we're probably not trying to print out the thing. We just want to return it as part of a method or something, okay? So don't forget about that one. Arrays, useful. Just a different thing that we do with templates sometimes is we put in a number. And it just proves that all templates are doing is a little copy paste robot, right? So it's going to take that 6 and it's going to use that to figure out how big to make some internal data storage item, okay? So we can't change the size of it once we create it, but at least it knows how big it is. and it saves us from having to, remember all the time how big a particular array is. Okay. Cannot initialize a size 6 array. Oh, right. Yeah, just heads up when you kind of do stuff like that. You might get a crash, right? So you can under initialize, you just can't over initialize. Okay. So all those two things are okay. Okay. And this would not work because it does not, this happens a lot, I guess. We think it's going to break this thing up, but it's not going to do it actually. So it wants it like this. Okay. Array allocation, just last couple things. So here's what happens when we have under allocated stuff. I think my animation here got a little messed up. So we're just going to have a 0 in there. Whoops. So I didn't finish my animation. This is actually going to be a 0, right? So it's going to do a nice job of initializing everything to some 0 value. Okay. Vectors, I know we all know these pretty good. We have push back, do not have push front, right? So vectors only allow you to work on the back end of them, okay? We can get a copy of what's at the front, right? But we can't actually push onto the front in any direct way, okay? Now, this one, I saw a few issues with our recent homework. Understandable, but we're going to do more of this. So remember that vectors start out empty, especially 2D vectors. So we can't immediately go to position 1, 1 and put something in there. We'll get a crash, okay? So we got to push something in there. And even that thing that we push in could be empty, right? So here's something that's empty. It's kind of had to skip past a lot of stuff there. But when we push in an empty row, that row still needs to have stuff put inside of it before we can use a double square bracket access for that, okay? So remember to add your rows in your double for loop. There's also a method you can look up called resize, which will do it for you in kind of one go. Some of you have figured that out, okay? It's a shortcut. But the double for loop will always get you there as long as you add your method or you add your rows as you go. Okay. Now the double-ended queue is like the vector, except we can push stuff onto the front or the back. So it's the most open-ended, flexible thing for working with things like decks of cards. Basically, it's a double-ended queue, right? That's why they call it a deck. It's not quite a DQ, it's a deck. Okay. We have square brackets and all the good stuff. So it's really a very feature-rich container, okay? And underneath, it's really doing some messy stuff, right? So if I push a 5 on the front of there, it's allocating an array and putting the 5 in there and saving a little space for next time. So it's doing a lot of messy stuff underneath in a pretty hybrid way so that we don't actually have to worry about that stuff. So there's no magic. Somebody has to write some pretty messy code down there. It's just not going to be us for that kind of stuff. Okay. So pop front, push back, great for deck of cards if we were allowed to use that for homework 4, but we're not allowed to. We have to use the list for homework 4. Okay. So the list is a doubly linked list. Okay. So there's no square brackets, no at, and you can use the reverse iterators if you want to go in the reverse direction. It's the most elegant way to turn around and go the other way, okay? And they're great for heavy insertion and splicing types of things because we don't have to reallocate like we saw with that DEQ thing just to kind of add more stuff in the middle, right? It's just pointer update stuff, okay? And forward list is a simplified version of list. So we won't go deep into this at all, but we don't have the ability to go in both directions. We can only go forward. We can't go backwards. So we couldn't go reverse iteration through that thing because it's got only one direction of pointers in it. Right? And no size, which is kind of crazy, but yeah, you have to actually iterate through it to figure out how many things you have. Okay. Deck of cards, no square brackets, no at, really similar to the list. So I won't dig into that too deeply. Let's talk about pairs because they are the foundation of our maps. And I think we actually might finish in a reasonable time here. We're turning the final corner, I think. So remember that what's weird about pairs is it's not a method, it's not a getter, it's a public data member. So we say dot first and dot second to get access to whatever the first thing is. The first thing could be a pointer, it could be a string, it could be a vector of something, it could be another pair, right? Same with the second one. So we got to look at the type to know what we're getting for each of these things, okay? So those are just public members of the class, okay? So there's a lot of ways these things get used, mostly the maps and our associative containers. So here we are again with all of our associative containers, mostly focusing on the set and the map, okay? So we want to generally use the count method to figure out whether there's something that exists in the set, okay? So it could be 0 or 1, or it could be greater than 0 in a multi-set, okay? It's like go fish. How many aces do you have, right? Where here there'd be only 1 or 0, okay? Maps, similar. Use that count when in doubt. If you're not sure, use the count to figure out whether something exists or not. Now, we didn't spend a lot of time with all these other variations, and we're not going to torture you with them, but it's good to know they're out there, and they're just slightly different in terms of whether they're sorted in order or not, okay? Here are our methods, big ones, right? There's no, for the associated containers, some of them support at and square bracket, really just map only, sets don't, right? Okay, and then begin and end, and all those other good things we've seen. These are generally part of all of our associative containers, which is good. Okay. Maps have the at and the square bracket. Okay, we got to watch out for those. We'll use more of the maps in the second half of the semester. Okay, especially for Facebook. So we'll be doing a lot of map stuff there. Now with sets and their cousin multi-sets, just a couple quick look at the code. There's our set creation. Okay, and those keys are going to be unique and ordered. So even though we have them unordered here, it's going to immediately order them because that's what it does. And it's going to, by default, order in an ascending way. Okay. And it's just going to be keys without values. Okay. Now, the really important thing to remember about sets is we don't have to go looking for something. They're optimized to tell us exactly whether they have something or not. So I can use either count or find. If I'm looping through everything in the set just to see if it has something, I'm wasting the best part of sets, which is the fact that they are highly optimized. So eventually I will start kind of pushing back and maybe taking off points if you are searching a set sequentially, because that's just not what we want to do with sets. They're really awesome and fast. So we can't go to a particular location, but we can just say, do you have that thing, right? How many do you have? Okay. So, and that's because it's a binary search tree, essentially, or a hash table in certain cases. Okay. So here's a little more code. This is for switching that around, pouring in a different data type there. Okay. To change the sort order, and then insertion of duplicates will be ignored, of course. Okay. So now we add a -1 and we just say, hey, if the count of that is equal to 1, then 1 is in there. Or I could say if the count of that is greater than 1, then 1 is in there, okay? We can also say if I try to find a -1 and I didn't run into the bumper at the end, then that is another way of knowing that I found it. It's pretty close in speed to this, but a little bit faster. Okay, so both of these are okay, right? And if we were working with a multi-set, it's just, I can have duplicate keys, okay? The main thing we don't want to do is this, searching for a key, right? for const auto ampersand this key of SA, look for it, right? Because we're just wasting the best part of a set, right? We just want to use find or count, okay? I mean, it's not the end of the world, but if you had a million of these things, it's going to take a whole lot longer than just using a find or a count, okay? Multi-set's pretty much the same thing, so I won't, bore you too much with this. It's just that we can have duplicate keys there, okay? Maps, we have pairs of information, okay? So the pair is comprised of a string and an int in this case, and that's our key and our value, okay? It's sorted by key, not by value, okay? And it automatically creates a pair for us. But if we want to insert something, we either have to say pair, or we have to say kind of that short form, that's a pair. And I like this way better over here, right? Curly braces makes a pair, so we're just inserting one pair, okay? And we can't, and we can say, hey, do you have a value for age, okay? But if it doesn't, it's going to create one for you, which is really maddening. So it's better to check with the count first and then say, oh, okay, give me the value via the square brackets, okay, for that particular key, okay. So here's the code, right? There's our string, int, variable name, right? Inserting a pair one way, right? So you can kind of see the correlation there of the key and the value, okay? Or that way, like we saw on the previous page, okay? And then print out the value associated with Apple, assuming it exists, okay? So as we saw with the sets, you do not want to search through all of your key value pairs. You just say, do you have a 2, right? Or, can you find a 2, okay? So count and find are the better ways to go for that, okay? And last couple ones, container adapters, stack, queue, priority queue, okay? So the key takeaways are just, what is it doing, right? We're pushing onto the top and we're popping from the top, okay? There's a top and a bottom. We can only push and pop and peek, right? We can look at the top to see what's there, okay? We can't iterate through it. So if we want to see what's in it, we got to destroy it pretty much, okay? And then pop, right, to take stuff off. Contrasting with our queue, which is kind of a left to right, line at a restaurant, right? Hungriest person first gets served. Actually, hungriest person, the one maybe the waiting longest, right? So we DQ or pop from the front, okay? And we NQ or push at the back. Those are kind of the main takeaways there, okay? So push and pop, front, get a copy, back, get a copy, basic Boolean stuff, getting the size and swapping things. Okay. And emplace we just haven't covered in this class, but it's good to know it's there. Okay. Reversing a queue, just an algorithm, right? It's a good one to know about. It just reminds us of how each of these things work. We sort of put stuff in the stack and then we NQ it, right? By pushing it back in the queue, okay? And now we get our reverse, okay? Pretty standard algorithm, okay? Priority queues, we won't go into what they are, but they are self-organizing, self-sorting, kind of. They kind of are like a heap of, things thrown on a table with the most important thing on the top. And every time we pop something off, they reshuffle themselves so that the most important thing kind of floats or bubbles to the top. So some of you might remember that from Comp 220, or bubbling up or bubbling down. And they do it very quickly, faster than any other normal sort because they're not fully sorted. So it's a very fast access, okay? So we push and pop and all the usual stuff. It's just that we always get the most important thing. And that is it. That is all the stuff we covered. That's a lot. I think if you just get a little time to look at the midterm, you probably be pretty good shape. So any questions on anything before we sort of wrap up? Okay, thanks everybody. Appreciate all your attention so far and your hard work. Good luck on Thursday and have a great midterm break if I don't get to talk to you. Okay. Thank you. Yes. Midterm open book.